Okay, good morning. Thank you. Thank you, Subinoy and others for inviting me today. So my talk is a little bit different from the others. I'm talking about dark matter on galaxy scales. And that is something I think is not there in the other speakers. Some of my talk will be very elementary, so bear with me because I'm going to start right from the beginning when Vera Rubin discovered the rotation curves. But then later on, I'll move on to talk about the shape of dark matter halos. I will not cover a very important topic in halos, which is the cusp core problem, the central geometry of the halo. But I will try to do the shape of the halo as much as I can. So this is the talk outline. In the beginning, I'll talk, like I said, early indications about dark matter in galaxies, and why I think everyone here should know about it, because if you want to detect dark matter, if you want to understand how it's interacting with the disk, with baryons, the best place to look at is our galaxy or nearby dark matter dominated galaxies. So if nothing else, at the end of my talk, I want you all to remember that low luminosity galaxies, dwarfs, are the best ones for dark matter detection and for understanding dark matter properties. Okay, so I'll talk about some work at the end of my talk. One of them is a project done by my PhD student, and the other project is me with several collaborators. Now we'll start right at the beginning. The beginning is when Fred Zwicky discovered that the dynamical mass in galaxy clusters is not the same as virial, as the luminous mass. Now, in galaxies, what we always talk about is the dynamical mass of galaxies, and the dynamical mass is estimated from the motion of matter. And in galaxy clusters, it's the simple random motion of the galaxies within the large cluster. And so back in the 1930s, which is nearly 100 years ago, he found that the visible mass, which is summed up from all the mass coming from the galaxies, was way, way smaller than the dynamical mass. And the dynamical mass he calculated using the virial theorem, which I'm sure you all know, the simple virial theorem, with perhaps a constant in the front due to the geometry of the system. Even now, we still use it to find out what is the dynamical mass of a system. Now, in the virial theorem, you have the v squared here, which is the velocity dispersion of the galaxies in the cluster. And you have r, which is simply approximately the size of the whole cluster. And the difference will give you the dark matter in the galaxy. Okay, so I wanted to actually show you, so this slide. So if you simply apply these numbers to a very nearby relaxed cluster of galaxies, the Coma cluster, you'll find that the visible mass in stars, and there's also some mass in a hot X-ray gas halo, that mass compared to the dynamical mass is much lower. It's at least 10 times lower. So you see here the dark matter mass, the dark matter halo of a cluster is enormous. And that tells you something about how our whole universe structure formation has assembled mass. Now, we've applied this dynamical mass, this kind of virial theorem approach. It's still applied to galaxy clusters. It's applied to elliptical galaxies. But there's one caveat, and that is that we don't know the exact shape of an elliptical galaxy or even a galaxy cluster. Because when we see these structures in the universe, then we don't often get the third dimension. For example, in elliptical galaxies, you don't see the third dimension. So there is a little bit of an if factor when you calculate the dark matter halo masses. Now, the centers of galaxies is also another place where the virial theorem is used, all the way in the center. So it's not related to this conference, because at the center of galaxies, we don't expect much dark matter. Dark matter in galaxies dominates the outer parts of galaxies. Now, since I'm talking about the evidence of dark matter from clusters, I have to mention the bullet cluster. And I think this, most of you, if you do a Google search on dark matter, you will come across it. Now, the bullet cluster is actually two large clusters of galaxies which are going through each other. And when they've gone through each other, the dark matter is associated with the galaxies, And so from lensing, you know that the dark matter follows these contours. So the dark matter halos have gone through, but the mass of the X-ray gas, the X-ray emitting gas, which is dissipational gas, that has settled into the center of the potential. So this is one of the best evidences of dark matter on the scales of clusters. Now, the second evidence comes from nearby galaxies, and this is what I work on. Now, galaxies are rotating disks of stars and gas, which are thought to be embedded in large halos. So, in the beginning, people didn't realize that there was this halo. They thought, okay, maybe the disk is rotating, but they actually found initially only this part of the rotation curve of galaxies. So they didn't realize until the early 70s that there was a large disk of rotating stars. Now, it's very important to discover the later part of that rotation, because the later part over here is differential rotation. The rising part here is the solid body rotation in a galaxy. So the differential rotation part goes all the way to the end. And initially, when it was discovered in galaxies, it was discovered from ionized gas, the H alpha emission coming from the interstellar medium in galaxies. And it was discovered by a very, very smart woman, Vera Rubin. And I must show her picture if we're talking about dark matter in galaxies. So Vera Rubin in the early 1970s found that the rotation curves of galaxies derived from H alpha extended way beyond the central inner few kiloparsecs. And she said that this was one of the indications of dark matter. And people found it very difficult to believe her. But at that time, in the early 70s, there was also some simulation theoretical work done at Princeton by Peebles and Ostreicher, where they did some crude simulations and found that disk stability, disks became stable only when there was a large potential surrounding the disk. That's an indication that there should be a dark matter halo to make disks stable when they are cold and self-gravitating. Now, I just put this picture to remind you that a rotating disk has Doppler shifts, both sides, red shifted and blue shifted. So if you see this kind of a galaxy and you want to look at the rotation in the galaxy, then if you take the whole emission, you'll get a double humped peak curve in H1 in neutral hydrogen or in the H alpha. And to actually calculate it, you'll probably have to take the inclination of the galaxy. You'll have to take a cos phi, which will be a radius vector to that point. And this V at the beginning will be the systemic velocity of the galaxy, which comes from the Hubble expansion. So using this simple formula, you can actually get the rotation curve, and then you will see that it's always flat in the outer parts. Now, how can we go from this rotation curve now to the dark matter halo? Now, that's actually, to do that, we actually have to take into account all the visible mass. The visible mass means the stars, of rotating disk of stars, and secondly, the gas. So if you take that baryonic component and then calculate V squared by R, which is equals to d phi by dr, and take their potential and then fit it onto the rotation curve. So for example, here, this will represent the stars. And you can see here the stars are following the solid body rotation in the center due to the bulge, and then they fall. The fall is because the disks of galaxies, the stellar disks, have an exponential decay. And so you will see this fall. You'll see it also a little bit in the gas, but gas kind of just follows in this way like a sandwich all the way to the outer parts. And if you then subtract it from the main rotation curve, you will get the dark matter halo of the galaxy. Now, this dark matter halo, as you can see, it's rising. So halos in galaxies dominate in the outer parts. And that's why looking at the outer rotation curves of galaxies or the outer equilibrium is so important. Now here, as an example, I've shown some rotation curves. Some of them are rising. They're still rising in the center. These are usually the dwarfs. And some of them become flat very early on. There is quite a variety. And apart from these rotation curves, let me also mention another two traces for dark matter in galaxies. The first is in our solar neighborhood. Now, this was done by Oort many years ago. What he did was he looked at the stars in the disk near in our own galaxy, and they should execute a kind of a simple harmonic motion about the plane. And he used nearby stars, K-type giants, to calculate that, and he found that there is some dark matter in galaxy disks. However, after SDSS came in the early 2000s, they found that no, it's not possible. We don't have dark matter in galaxies. Those stars were not detected by Oort, and that's why he thought that there was dark matter. However, now with better and better observations, we are beginning to realize that there must be some disk dark matter, which is even separate from the halo, which is associated with the galaxy disks. So that is the dark matter. It's kind of historical in our solar neighborhood. Now, dark matter from the population of stars which reside in the halo is also a very important way to detect the dark matter distribution, and it's done very often for our galaxies and nearby galaxies, where you can actually detect the globular clusters or even some of the stars in the halo. Because the stars in the globular clusters, they'll follow these paths, which are loop orbits or plunging orbits. Sometimes they're a little bit like boxy orbits, but modeling their orbital structure, you can go back to the potential and hence determine the potential of the dark matter halo. So as an example, I'm showing this here, picture here. This is our Milky Way disk plane. And you can see there are numerous filaments all around, and these are called tidal streams. Now, tidal streams is something it's recent in the last 5 years we've been discovering, and these streams are remnants of nearby satellites which are merging with our galaxy, and their path as they come, their tidally disrupted stellar stream is a very good way to model the potential of our own galaxy halo. And this has been done by the Gaia instrument, Gaia Space Telescope. And this has amounted to a large amount of data, which can probe not only the outer parts of the halo of the Milky Way, but also towards the center. So this is also a very important part. Stellar streams with better and better optical imaging can also be used to model the outer halos of nearby galaxies. For example, here you can see an edge-on galaxy here, and you can see a polar ring kind of stellar debris here. And this kind of a structure can be used to model the halo of the galaxies. So lastly, I'll mention gravitational lensing. Gravitational lensing is a very powerful tool, and it was not exploited until about 10 years ago so much. Now, with better and better galaxy optical surveys, we can detect very beautiful lenses. For example, the Subaru All-Sky survey found a lot of beautiful lenses like this. And these lenses can tell us more about the halo population in the redshift space. And I've just shown what lensing means over here. And over here, the famous bullet cluster, where the evidence for dark matter came mainly from the lensing. Now, where do we look for dark matter halos in nearby galaxies? Where do we look? So I want you to remember that the best place to look are the low luminosity galaxies, because it's been shown from numerous studies that the low luminosity galaxies which are not bright, do not show bright star formation, they are the best places to look for dark matter halos, because low luminosity galaxies are dark matter dominated, which means that the mass of the dark matter in these galaxies is sometimes even 10 times the mass of the visible matter. Now, why these galaxies don't form stars is simply because their stellar disks are often very diffuse. They're not very strong. So the self-gravity in the disk is not strong. It's the dark matter halo that has probably caused this. It is also possible that the dark matter halo spin has caused the disks to kind of spread out, and therefore they are very low in density. So as an example, this galaxy, you can see here, the black points in the center represent the stellar disk, and the stellar disk is way in the center. And outside here, you can see the neutral hydrogen. So the neutral hydrogen is kind of just hanging in there. It's really not associated that much with the stellar disk. So the question would be, what's holding it up? So that would be similar to the dwarf galaxies here, where you again see a small stellar disk and the enormous H1 neutral hydrogen disk. This neutral hydrogen disk is about 6 times the size of the small stellar disk. And if you look at this galaxy, KK46, and you look at its velocity field is very regular, and its velocity field gives you a rotation curve which shows that is extremely dark matter dominated. Now, why is it important for generally the disk? Why is the dark matter halo important? So when we just calculate the stability of a disk, when the disk is rotating, then what happens is the gravitational force is balanced by the centrifugal force. So we can use the simple equation GMM by R squared is equals to V squared by R. So it's a dark matter halo which is giving the stabilizing force for the rotating disks. Now the vertical support is also very important in a disk. Now in the vertical extent, so if you have a thin disk of stars, then the stars will be oscillating up and down as well as rotating in the disk. Now the vertical potential should have a contribution not just from the stellar mass itself, but also from the halo mass. Now if you go further and further in the outer parts, you don't have much stellar mass, then the dark matter halo mass becomes very important for the vertical support of the disk. And we have exploited this fact, which I will show in the later slides. So this is why I mentioned here what happens in regions where there is very little stellar disk. Then it is the dark matter halo which will be important for the vertical support. Now here are some examples of what we call the low surface brightness galaxies. These LSB galaxies, as we call them, are probably the most dark matter dominated galaxies, and they are a field of their own in studies of galaxies. Now, LSB galaxies can be of 2 types. They can be like these massive LSB galaxies, which I've studied with the GMRT, where you have a huge neutral hydrogen disk and a small stellar, diffuse stellar disk. These galaxies are some of the largest galaxies, but these are called the giant LSB galaxies. You also have another variety, which is the dwarf LSB galaxies. The dwarf LSB galaxies are the galaxies that have been used for dark matter detection experiments because they have very, very little dark stellar matter. Most of the mass appears to be dark matter. So we did one project and Subinoy was involved in that. This was just to give you an example. This was done by Pooja, where we looked at the Fermi data, because if you have annihilation between dark matter particles, then some gamma ray emission is expected. And I think this has been used a lot and done a lot in the literature, but you can only get limits to the dark matter content. You can't really obtain any detection. Now we'll move on to the second part of my talk, which is about the halo shapes. The halo shapes of galaxies. Does anyone have any question about the previous part? No? Okay. So I'll move on to the halo shapes. Now previously, about 20 years ago, halos of galaxies were all thought to be spherical. So it's a very nice mathematical format. We have a nice spherical halo and we have a rotating disk. So we can put the potential of the disk, the exponential potential, and a nice spherical potential for the halo. And initially, when the halos were studied as spherical potentials, they were also considered to be rigid. But in the last 20-25 years, simulations now take halos to be live. That means halos are composed to be made up of millions of particles, just like the stars in the stellar disk. And they are often also taken to be rotating. So they have an angular momentum, they have particle distribution, they of course have their own profile, which is usually taken to be kind of a steep, or we call cuspy profile in galaxies. Now, let me just take you, before I talk about the cosmological simulations, let me show you about the observations of halo shapes. Now, as I mentioned earlier, tidal streams or basically galaxies which have been disrupted during the merger with our galaxy or another galaxy. Tidal streams are a great way to investigate the halo. One form of a tidal stream is a polar ring. A polar ring is basically another galaxy which is coming and merging with the galaxy. And instead of merging in the axisymmetric plane, it falls into the vertical plane. So it's called a polar ring. And polar rings are rare, but they were discovered about 25 years ago. And several of them, this is one of the best examples. It's a stellar polar ring. This is the galaxy disk, and this is the huge stellar ring. So the polar ring, the velocity distribution of the stars and the geometry can be used to probe the halo potential. Now, in these studies, they had conflicting results. Some studies suggested that the halos were quite flat, E6 to E7, and some of them thought that the halo was more spherical. Some studies of our galaxy suggest that our galaxy has a prolate halo, but most of the studies nowadays suggest our galaxy has a spherical halo. Now, another way to examine what is the shape of galaxy halos is to look at edge-on galaxies. So edge-on galaxies, some of them, when you move to the outer parts, they become warped, like bent. Now, the warping happens in the neutral hydrogen, because the neutral hydrogen is very light, it's diffuse, and it kind of responds very fast to any kind of perturbation. So you could have, say, an S-shaped galaxy with the central part being the disk, with little flat, and turned up at the edges, something like this. Now, this may seem quite small, but it is quite significant if you do a more deeper analysis of the shape. And I'm showing here a very famous study by Olling. And what he found is that this galaxy 4244 was very, very oblate. And this was in the mid-90s when it was thought that most galaxies had spherical halos. So I think this is a really remarkable study. But since it used observational data, it did show that you can have oblate halos. Now, another way to look at the halo potential is to look at the distribution of stars and globular clusters in galaxies. And here I'm showing you two views of our galaxy distribution. This is in the plane, which is nearly spherical, and this is in the Z plane. And you can see here, it looks like it's cigar shaped. So it looks a bit like a prolate halo. So many studies have suggested that our galaxy has a prolate halo, but it's still not clear. Because another thing you have to remember, that the shape of a galaxy halo can be a little bit maybe oblate in the center, but as you go further out, the shape can change. And so it's a complicated problem, and that's why simulations are very important. And this I will not talk about since I mentioned stellar streams earlier. Now, simulations, I'll just briefly go through what simulations have done. Simulations are very famous ones like the Eagle simulation or the TNG50 simulations clearly show that having a live halo is very important, and that in cosmological simulation, halos evolve with time. So there will be galaxy mergers, galaxy interactions, which will disturb halos, which will make them not virialized and ideal systems like we treat them theoretically. So only really for the galaxies which are very isolated that we can treat them like that. Now, the early simulations, very early ones, Dubinsky in the mid-90s, they showed that if you have a galaxy halo forming at early epochs, then what happens is as the halo is present, but as the mass falls into the halo, what it does is it affects the halo potential, and it makes what we call the halo more axisymmetric in the disk plane. So the halo B and A axis, which is in the disk plane, is found after you have the gas infall and the star formation. It becomes circular. But the C in the Z direction, the C by A axis is not always equals to 1. So you can have halos which will have B by A close to 1, but C by A can have a variety of values. Now, if you come 20 years later, the cosmological simulation, this is the black one here is the dark matter only. And the red one here is the simulation that includes all the baryonic physics. Now, when I say baryonic physics, I mean not only star-gas interactions, but also nuclear activity, stellar activity, which is happening in the galaxy. Because in the center of the galaxy, for example, if you have a supermassive black hole, it starts accreting mass. Then what it will do, it will push out winds. And when those winds go out, it will drag matter. If it's a very strong wind, it will drag matter with it. So it may alter the central potential of a galaxy. And so that's what they included in these simulations. There are several of them now. And here I'm just showing you a result by one of these simulations. And I'm showing you what is the ratio of the axis, the C by A and the B by A. The B by A is close to 1, but the C by A can have a variety of values. So this is also another paper which shows that for a lot of galaxies, the C by A can be close to 1, and for some of them it can vary. So it is a variable quantity, the C by A. So now how the halo concentration, I won't spend time on this since I'm a little short of time. Okay, so what we have done now, let me just quickly talk about the work that I've been doing. I've been using the vertical equilibrium of galaxy disks to try and understand the halo properties. Now we know that when we have a galaxy which is face on, then what we are seeing is the velocity dispersion in the z direction. The geometry is like that. So if we have face-on galaxies, then we can use the face-on galaxy, the z direction, to obtain the z direction velocity dispersion. So this is what we did in this work. And a simple hydrostatic equilibrium was kind of assumed for the outer part of the disks. In the outer part of many of the isolated galaxies, there is no star formation. So you can imagine that the disk is in equilibrium. So if we look at such an equilibrium disk face on, then we will be able to get the velocity dispersion in the z direction. And we can use a hydrostatic equilibrium equation like this. So 2-3 years ago, what I did was I first looked at the velocity dispersion of some large galaxies, dwarf galaxies, and I found that there is excess matter, which is dark matter, in the outer parts of these disks. And it has to be there because we need the vertical support. And later on, recently what I did was I took that dark matter, that excess dynamical mass in the outer parts, and I modeled it as halo dark matter. And when we model it as a halo, then there is an oblateness factor or a Q, which is an axis ratio factor that comes in. And this Q factor can be easily associated with the velocity dispersion, which we get from H1 observations and the distribution of the gas in the disk. And we can assume the rotation velocity from some empirical relations, which again have been based on observations. So nearly all of the inputs to this equation are coming from observations. And these are the galaxies, so I'll skip that. So what I found is, and the interesting result is that I found that all the gas-rich dwarf galaxies are oblate. And that I think is a very interesting result. It matches also with what simulations suggest. Simulations also suggest that the dwarf galaxies have larger angular momentum or spin. And when something spins, then matter spreads. And when matter spreads, it becomes a diffuse disk. So this is one of the most important results that we have. The second important result is that the oblateness has a correlation with the stellar mass. So this means that the massive galaxies, the galaxies which have stellar mass 10 to the power 9, 10 to the power 10, and our own galaxy will have prolate, spherical or close to prolate halos, whereas the small galaxies will have oblate halos. And I've been also studying this in simulations, and this is a student who's just graduated, Ankit Kumar. And what he did was he took n-body simulations where the oblateness of the halo was varied. And when you make the halo flatter, what you're doing is you're putting more mass into the disk. So the disk has not just stellar mass, it also has dark matter mass. It makes the disk hotter. More mass, more velocity dispersion, kinematically hotter disks. And we know from galaxy simulations or just understanding of galaxies that when galaxies become hotter, you cannot have instabilities easily forming in them. Because to have a good spiral structure, to have a nice bar in a galaxy, you should have a cold self-gravitating disk. So this he found out, and I could not, and you can see here, he's made a cartoon here of the different kind of halos. This is prolate, this is very oblate. And the second thing, apart from bar formation, the second thing that he studied was the bar buckling. The bar buckling is basically, it's the bending of the bar, which comes due to secular evolution, the evolution of the bar. And that is affected if the halo is oblate. And we do find that our results match some of the observations that we see. But it is a little hard to match with observations of bars. So I think I will stop here. I will show my summary slide. Maybe I'll just say it while you're thinking of questions. The ionized gas and the neutral hydrogen gas, they are the main tracers of rotation and hence dark matter containing galaxies. The stellar disks are embedded in live dark matter halos in most simulations. Halos can have different shapes. Our results show that the gas-rich small dwarf galaxies preferably have oblate halos rather than spherical or prolate halos. And the oblateness Q shows an increasing trend with stellar mass. I think I'll stop.
Thanks, Mousumi, for such a great talk. So let's start with the question. There is this class of dark matter called fuzzy dark matter or ultralight dark matter, which is designed to solve this core cusp problem. So you cannot squeeze it because they are very light. Now, how does that class of dark matter, I mean, compared to CDM, do with the halos? So I would imagine that you cannot squeeze it, you cannot make it oblate because they are quantum objects. And
so I don't think it will be squeezed that far. Even if a halo is oblate, I don't think the particles are that close that it will matter what is
the wavelength of those particles are the size of a galaxy. So they are quantum objects.
Okay.
So you cannot squeeze them. So
yes.
There is an extra pressure.
Yes.
So is there a quantitative study that you can?
I think some of the studies of self-interacting dark matter. Those are different. Okay. So I think Subinoy can answer this question better.
In my talk, someone asked whether the fuzzy dark matter solitons can be oblate or something, and I think they actually can. I think I have read somewhere that you can get them spinning, and you can have some oblateness. So I don't know for sure, but I think you could.
No, I think solitons are those are post-condensates. These are different objects. This fuzzy dark matter basically is that the quantum wavelength is the size of the galaxy.
But what?
That's why you do not have a core, because the uncertainty principle which prevents you from squeezing that.
But I think once you're outside the soliton radius, it would behave like CDM, and you could have all the same properties.
Yeah, about 1 kiloparsec. Okay. So maybe beyond 1 kiloparsec, there will be CDM.
Yeah, but I think this can be something we discuss in the afternoon as well. So both fuzzy dark matter and self-interacting dark matter predict cores generically. And so once you have tracers out to the outer parts of the halo, many of these things can be tested. Even the shape, for example, if you have self-interacting dark matter, the shapes typically become more spherical just because you have momentum exchange coming from different directions. And so if you have halo shape measurements out to large radii, again, that's very useful for constraining self-interacting dark matter models. So, I didn't frame it as a question. I thought this is something we can probably discuss during discussions in more detail.
Hi, thanks for the nice summary and talk. So I wanted to ask two things. So one is the warp-shaped edge-on galaxies that you see. So you related to sort of the the shapes of halos, is it also, so you also get these warp shapes when you have galaxies falling into, say, clusters and they're getting
Yeah, yeah.
distinct-
So I think they're two different. So one of the like early explanations for these warps is that if you have the halo spin axis, okay, if that is different from the spin axis of the stellar disk, if there's a misalignment, then as you go further and further out, the halo is dominating the rotation, and it'll be like this, whereas in the center it'll be like this. So that's the misalignment of the halo and the stellar disk. But for
like central galaxies and
yeah,
okay.
but for galaxies that are falling into the halo cluster potential, then I think there's something called ram pressure effect and tidal forces.
Stripping, tends to create.
Yeah, a U-shaped kind of a structure in maybe the
That
H1.
would be the ram pressure. But
Yes.
even just simple, dark matter tidal disruption tends to also create these.
Oh,
warps.
okay. Okay. Yeah.
The other quick question I had: do you know if the galaxy without dark matter, which I've been talking about, if that has been observed with the fixed survey, or if GMRT can observe?
No, so those are the what they call ultra diffuse galaxies, UDGs. So it's so a lot of UDGs don't have gas. So I know that the Narim Patro he's observed a sample, but I've noticed in the literature it's like 50-50. Some have gas, some don't have gas, but they have been observed.
Thanks.
Yeah, okay, so thanks for this nice talk. So we get to know about the signature of dark matter from these various kinds of observations, like galaxy rotation curves, bullet clusters, and all those things. But can we actually guess the mass range of the dark matter from these observations?
So we have to make an assumption here, because you mean the dark matter halo mass, right?
Yeah, yeah.
Yeah, so we have to make an assumption. So halos are supposed to end as what is called the R200 radius, where the density of matter is 200 times the ambient density of matter in the universe, R200. So if we, and there's a formula for that, for getting the R200. And so if you know the R200, then you can just imagine that the rotation is extending out to R200, and then take that to be the halo mass. That's usually much, much higher than the stellar mass. It's usually huge.
Okay, and and what about the dark matter mass? Like for WIMP, we say the mass is like at the electroweak scale. For fuzzy like dark matter, so it's like sub electron volt order of mass. So this kind of mass I'm talking about.
Oh.
So is it feasible to guess the mass from this kind of observations?
No, I don't think so. No.
Okay. Okay. Thank you.
Yeah, hi. Over here. So I just have a quick question. So when you fit a oblate or prolate model to the rotation curves, do you fix the axis of oblate prolate dark matter halo to be the axis of stellar disk, or you make it a free parameter?
Yeah, we make it, so we don't, in this study I don't use the rotation curve, I use the velocity dispersion, because it's a face-on galaxy. So I can't detect rotation, but I can detect the Z direction velocity dispersion. Okay. And there we make an assumption that the disk halo is B by A is equals to 1.
Okay.
Okay, so so what we are tracing is only the Z direction flattening or axis ratio, Q, C by A.
So you assume that the stellar disk Z axis is aligned with the prolate
Yes,
or
yes.
but that necessarily, it should not, it may not be necessary.
True,
right?
true. It's not, it doesn't have to be true.
And if it is misaligned, that is it a kind of a signature that the dark matter has angular momentum, so that prolate?
Yes, that's a good point. Yeah, it would actually. If you have two like observations of, say, this oblateness, and you try to match them with, say, another observation, put parameters for your angular momentum of the halo. Yeah, that would be a good way to constrain it.
Okay, thank you.
Okay, so we end the morning session here, and further questions if you have, we can take it over session or in the discussion session in the afternoon. Okay, let's thank Mousumi again.